Good evening, everyone. My name is Aditya Sharma, and this is a power plant system engineering course being conducted by Department of Mechanical Engineering, IIT Guwahati, under the NPTEL program. And we are into the seventh week of this course. And related to that, we are conducting this tutorial number 7. Okay, instructor for the course is Professor Niranjan Sahu, and I am a teaching assistant. So Professor Niranjan Sahu is from Department of Mechanical Engineering only, and I am also a research scholar here. So we shall wait for another couple of minutes. After that, we shall start today's session. So we can start with today's session. So today's session again is on vapor power system. So this is the third part. Okay. So we have discussed, I believe, in the last tutorial. Yes. So we have discussed boilers in the last tutorial, right? And now here we will be discussing the fuel, right? Uh, which is majorly coal. Okay. and then the combustion related to coal. So the discussion, all the discussion revolves around this only. Okay. Uh, right. So we will move ahead in the same fashion as we have been doing in the previous sessions. So one lecture and then questions related to that lecture, and then another lecture and questions related to that, and the same way. So there are two lectures in this week's content, right? So lecture number 15 and lecture number 17. So let's see the topics one by one of lecture number 16. Okay. So the topics are like this. First, coal has been discussed, and then analysis of coal has been done. Then, how can we fire the coal? So, different methods have been discussed, and after that, fluidized bed combustion. So, this is the major method that we use to combust coal. Okay, so in your lecture number 16, fossil fuels. Okay, so coal is one type of fossil fuel, right? So there are grades, grading of coal is done, right? Grading of coal is done based on the carbon content and moisture content and other content in your coal, right? So the highest grade of coal is your anthracite, right? And the lowest one is your lignite, right? So this is about grading. Okay. So grading also is related to the heating value of coal, right? So heating value we give in megajoules per kg. Okay. So this is a brief introduction has been done about coal, right? Then is your second topic is coal analysis. So there is one analysis that is proximity. So analysis basically means that we want to better understand the coal that we have in our hand. Okay. So what is there in proximity analysis? So here we have mass percentage of fixed carbon. One is this. Then volatile matter, then moisture, then ash. So the carbon content is the thing that is of our use, right? And at high temperatures, this volatile matter won't remain with the coal. Okay. Then is your moisture content and then ash content. As ash content has no heating value. Yes. So this is what we do in proximity analysis. Now in your ultimate analysis, we have elements comprising coal. So this is a more detailed analysis of coal, where we take into consideration the different elements that are present in coal, right? Then we consider ash, then we consider moisture also. Okay. So in elements, we have carbon, hydrogen, oxygen, nitrogen, sulfur, right? So these are elements. Then, but also we see moisture and ash also, right? So there are mass fractions in the coal that we have. Then is concept of heating value. So what is that? So we have some fuel, let's say, right? And after combustion, it will have air plus fuel products. And these products will have some temperature after combustion. Initially, air and fuel have some temperature. After combustion, products have some temperature. And related to this temperature, the products have some energy. And when these products come to a lower temperature, that is related to the initial temperature of air and fuel. In that case, the heat that is released, right? That is the heating value basically of a fuel. Then there are two types of heating values. One is your high heating value. Then is your low heating value. Correct? So what is high heating value and what is low heating value? So again, let's see. So let's say we have fuel, air, products, right? In the products, we will somewhere have water also as a product. So when hydrogen reacts with oxygen, it will give water. Okay. Now this different heating values are related to somehow water. So how? So in case your water is in vapor state, so the energy that has been lost in vaporizing the water, that is latent heat of vaporization, that is now not in our hand to use, okay, that we have lost. But in case your water condenses, then the latent heat of vaporization can be added to your heating value of the fuel, because that is still in our hand to use for our purposes, right? So this basically is the difference between high heating value and low heating value. So when the water is in condensed state, that is your high heating value, right? So high heating value basically is low heating value plus latent heat of vaporization, right? Okay. So this is about your coal analysis. Then is your coal firing. So different types of coal firings. So initially, it has been discussed that there used to be manual feeding, right? In your furnace, there used to be manual feeding of coal, right? Then there is one type of firing, that is pulverized coal firing. So what happens in pulverized coal firing? Basically, what we do, the coal we have, so we crush it, right? We crush this coal, and in this form we use coal for firing, right? So that is your pulverized coal firing. Then is your cyclone furnace firing. So what do we do here? So by means of centrifugal motion, what we do, we try to better mix our fuel, that is coal, with air, right? So that we do by some device that centrifuge the fuel coal for better mixing, and that is known as and the system in which we do this is known as cyclone furnace, right? So this is cyclone furnace firing. Then is your major type of firing or combustion, that, that is fluidized bed combustion. So this is your major type of combustion. So what is there in fluidized bed combustion? So structure is something like this. So we have air entering from here, right? By means of some fan, right? Here is our bed, right? And then here are your tubes, right? Your fuel is fed from here. Then one more thing is also present here, something like this, okay? And this again goes to here. So what happens in fluidized bed combustion? So it has components, okay? So first is your fluidized bed, right? So this is your fluidized bed. And somewhere here we have air distribution grid. Okay. And this is your cyclone separator. So what we basically do is we try to fluidize the fuel, right, by means of the air that we are giving from here, right? And this is plenum chamber, from where the air goes in upward direction, right? So we feed fuel in the this fluidized bed, right? And then by means of air, this fluidized bed fluidizes, right? It fluidizes the particles of coal that are present in the bed, correct? And then the combustion here is initiated, firing here is initiated, and then the products move upwards, right? But one more thing is also here, that we add calcium carbonate also here with the fluid in the fluidized bed. And what is the importance of that? So this is basically to neutralize your sulfur dioxide form, right? Because we don't want sulfur dioxide to be in our products, right? Because it is toxic, right? So for that, what we do is we add calcium carbonate. It reacts with your sulfur dioxide and gives some uh, product, right? Inert product, which is not as uh, not to say this way, but it can, so we can capture this final product, right? That reacts with your sulfur dioxide. And this way we can eliminate this sulfur, right, from our combustion products, right? Then there are expressions for your how we can equate the weight of these particles that are there in the fluid bed with the drag force that these experience, right? So when air flows in upward direction and fluidizes these particles, so how we can equate the weight of particles with the drag force, so that the particles because the particles are there they're in equilibrium, right? And then the velocity velocity required for fluidization, so how we can calculate that. So this has been discussed, and expression for it has also been given in your lecture, right? Lectures content. Then one parameter is void fraction. Void fraction basically when your particles, fuel particles have fluidized, in that case some space. So if this is your bed, right, so there will be, this is in fluidized state, right? There will be some space will be left, right? So this all space is left, just a representation. So this, to quantify this space, right, we define void fraction, that is alpha, okay, which basically is alpha is 1 minus rho b by rho s. So rho s is the density of your particles, right, fuel particles, and rho b is your bulk density, if I remember it correctly. The name, if I remember it correctly. The meaning is that when your bed is in fluidized state, in that scenario, what is the density of your whole, if you take the whole volume of your bed, right? So that is the meaning of this rho B. Okay. So this was your fluidized bed. Okay. Now we shall move towards questions. Okay, so this is your first question, which says that which of the following is the highest grade of coal. So four options have been given. So please have a look at the four options. First option is lignite. Second is anthracite. Third is bituminous, and fourth is subbituminous. So the highest grade of coal is your anthracite. Okay. So the moisture content and other impurities are less in this type of coal, and the carbon content is very high. Okay. And your bituminous is your average grade of coal. So B option. Now moving on to next question. So it says that the first geological step of coal formation is what? So if you see the options, first option is lignite, anthracite, bituminous, and peat. So we know that the first three options are the type of coal, right? And then the fourth is your the answer. Okay. So the when your coal starts forming, in that case, the first form you get in coal is your peat, right? So we call it peat. Okay. So the answer to this is peat. So that's fact-based two questions. So D is the answer to this question. Now the third question is on heating values. So we have discussed high heating value and low heating value. So this is based on that only. So this question says that the difference between high heating value and low heating value of a fuel is equal to. So four options have been given. One option is your latent heat of sublimation for fuel. Then is your latent heat of vaporization for fuel. Then is your latent heat of sublimation for water. Then is your latent heat of vaporization for water. So which will be the correct answer to this question? So in the discussion of heating values, we have seen that this latent heat that we talked about and the difference between the two heating values. So this is related to your water only. Okay. And that too the vaporization, latent heat of vaporization. So if you see the options, D option comes out to be the correct option. Okay. So if you see here, high heating value is low heating value plus latent heat of vaporization. So your low heating value is high heating value minus latent heat of vaporization. Or the difference between high heating value and low heating value is your latent heat of vaporization. Okay. So D option was correct. Right. Then moving on to next question. Which of the following is not a part of fluidized bed combustion or combustor? So we have air distributing grid, air distribution grid. Second is your pulverizer. Third is your cyclone separator. Fourth is your plenum chamber. So plenum chamber is the space from where the air is directed towards your air distribution grid, right? And above your air distribution grid, you have your bed. Okay. Then cyclone separator is used to separate your, remove your sulfur, right? And also the unburnt fuel that comes with your combustion products. Okay. And that unburnt fuel is then again redirected to your, so if you this see the directions here, so here see this direction. So from your cyclone separator, the unbound fuel is again redirected to your bed. Okay. So your bed is in, I have marked in your in the dotted, between the dotted lines. So air distribution grid is part of your fluidized bed combustor. Cyclone separator is also part. Plenum chamber is also part. But if you see a pulverizer, we don't use a pulverizer in your fluidized bed combustor. Okay. So this is the answer to this question. B option, right? All right. So this was question number 4. Then we have question number 5. So please read this question for a while. So I'll be back in just 2 minutes. Yes. So question number 5, it says that in a fluidized bed combustion, sulfur dioxide formed in a combustion is removed using. So I was talking about removal of sulfur. So how we do it? So this is whether this is calcium carbide, calcium sulfide, calcium carbonate, or calcium sulfate. So in your combustion products, what happens is you have sulfur dioxide in your products. So how do you deal with sulfur dioxide? Because this is unwanted. So you add calcium carbonate in your fluidized bed, right? So this just gives rise to, so if you balance it with oxygen, this will be, I believe, something like this. Okay. And this is captured by your cyclone separator. And this way we remove the sulfur from our products, right? So this was question number 5. So what we are adding? We are adding calcium carbonate. Option C. Sorry. Right. Then moving on to next question. Question number 6. So let's read this question. So it says that the minimum fluid velocity necessary for fluidization in a fluidized bed combustion can be calculated by equating dash force on a particle due to motion of fluid. So what we can equate with the weight of the particle, which force we can equate with the weight of the particle to find minimum fluid velocity necessary for fluidization. So I have drawn here this diagram. So if you say your fluid or air is moving in this direction, in that case, these particles, right? Every particle, so these particles will, so if I draw one particle here, so, and velocity is in this direction, right? So this particle will have weight in this direction, right? But air is moving in upward direction, right? So for equilibrium, this weight is being balanced by the drag that this particle is experiencing because of the motion of the fluid. And fluid in this case is air. Okay. we do the same thing. We equate these forces, right? So what we do here is question number 6. We equate, so this is coefficient of drag. Okay, so equate this drag with, so we somewhat like it, write it this way. Okay, so CD is your coefficient of drag. F is for your weight of your solid particle. Okay, rho v is your bulk density. U is your fluidization velocity. Right, and AC is your area related to your frontal area, cross-sectional area related to your particle. Okay, which basically is the area of circle, right? So if r is the radius of the particle, then it will be pi r square. Okay, this is your weight of particle. So this way we equate drag force and the weight of particle. Okay, now if you see the question, A option is the correct option. So this is a true or false type of question. Question number 7. So this is on void fraction, and it states that the void fraction of bed in the fluidized state in a fluidized bed combustor is the fraction not occupied by the fluid. The fraction of space so void fraction of bed in fluidized state in a fluidized bed combustor is the fraction of space, right, in your bed that is not occupied by the fluid. So whether this is true statement or not. So void fraction basically is the space that is occupied by the fluid and not occupied by the solid. But the statement says that the space not occupied by the fluid. Okay. In that case, this is a false statement. because it should have been is the fraction occupied by the fluid. Okay. Or not occupied by solids. If it had been written in that manner, in that case, the statement would have been true. But here it is false. So this was your question number 7. So this question number 8 is a numerical answer type of question. Please read the question. It states that for a fluidized bed, the bed particles are fluidized by air under ambient conditions. The density of loosely packed bed. Loosely packed means when the particles have fluidized. 1632. When the particles are in fluidized state, it is 1632. And in and the density of solid is, so the density of particles in general is 2638 kg per meter cube. So we need to find out the void fraction. Okay. This is your question number 8. So bulk density here is 1632 kg per meter cube. Density of solid is 2638 kg per meter cube. So alpha, that is void fraction. So your void fraction is 1 minus rho b by rho s. Okay, which is also this. So you have 2638 minus 1632 divided by 2638. So this comes out to be 0. Just calculate it once. Yes. So this comes out to be approximately 0.38. So this is your void fraction. Okay, so this much space is your fluid in terms of fraction. So alpha is this, right? This. So this is your question number 8. Okay, 0.38. Then we have next question. Okay, question number 9. So we shall solve this. Forgot to change the, here this is 9.2 tons per hour. Okay, okay, yes. So, so since it's already 1 hour has passed since we have started this session, so we shall take a short 5 minutes break and then we can start with the remaining session. We can proceed with the remaining session. Okay. Okay, so we can start with the session, correct? So we have a numerical in our hand. Yes. So we need to compute the capacity of a motor that is required to run a fan. That is forced draft fan. It will be used at this temperature, and about the coal data has been given, the mass fractions of different elements, and the rate at which the coal is being given to your combustor, that is also given here. And in your combustion process, the percentage in which your air is in excess has been mentioned, and the pressure in the plenum chamber, that is there, is also mentioned, and the efficiency of the fan has also been mentioned as 0.58. So we'll solve this. So I hope you remember that we have discussed forced draft fan in your boilers also, right? Where we have discussed steam drums, right? So entry of the air is through your forced draft fan only, right? Yes. Yes, though I have not drawn the diagram, but okay. So power requirement for FD fan is mass flow rate of air into specific volume of air into pressure drop across the combustor. Okay. And then is efficiency of your, sorry, the pressure in your plenum chamber. Okay. Then do we have mass flow rate of air given? So what do we have in our hand? We have temperature for air 298 Kelvin. Pressure is 101325 Newton per meter square. Okay. Then efficiency is given as 0.58. And the pressure difference, delta P is 1.5 kilonewton per meter square, right? So all this has been given to us. Then coal feed rate also has been given. That is, coal is your fuel. So that is 9.2 tons per hour. This is kg per hour. Okay, that is 9200 kg per hour. So all this information has been given. But if you see, mass flow rate of air is not given, specific volume of air has not been given. This is given, this is given. This we need to find out. So what we will do, first we will find out specific volume. Okay, using the perfect gas equation. So air is RT of air by P of air. So R is 287 for air. Temperature has been given as 25 degrees Celsius. Pressure is okay. So if you calculate this, this will come out to be 0.8440 meter cube per kg. Correct? Then next what we will find out? We'll find out mass flow rate of air. But how we can find out mass flow rate of air? So what we will do is, first step is, for mass flow rate of air, what we will do is we will find the total rate of for your air, right? And from there we can find out, because this is per unit of fuel. So this is like this, right? But then what is WT? WT is, so we have seen this in our slides. It is this. Though I'm using this expression in lecture 16, I believe this expression is there in lecture number 17. So please, if it is in lecture 17, you can find it there only. Okay. So now for carbon, it is given, hydrogen, sulfur, all the fractions have been given, right? And when you place all these here, what you will get is 9.907 kg of air, right? But this is with respect to what? Fuel, right? So for 1 kg of fuel, how much amount of air is required, right? And in that air also we need oxygen, right? So this estimate is based on the fact that there is 23% of oxygen is there in your air, right? So this way it had been derived in lecture number 17, I believe. And now we know that okay, we know that we have 22% air in excess, right? So in that case, so this is stoichiometric, okay? Stoichiometric, that is ideal case. But in reality, we have air in excess. So this will be 9.907 into 1.22 because it is 22% excess. So if you multiply this, you will get this, okay? Right? Now coal we have written, right? So now using this A, so Wt equals to mass flow rate of air by mass flow rate of fuel. Air we have to find out, Wt we have, sorry, right? So this is 12.08. So for fuel, this is 9200 kg per hour, right? Now R we can convert in seconds. So this comes out to be this. So this is equal to your mass flow rate of air. So mass flow rate of air equals to, if you calculate this, it will come out to be 30.87 kg per second. Okay. So now we have mass flow rate of air. We have specific volume. Now we can calculate the power requirement. So is mass flow rate of air is 30.87, specific volume is, right, and this is 1.5 kilonewton per meter square. So I'll keep it in kilos only, 10 raised to power 3. So if you work this out, this will come out to be 67.381 kilowatts. Answer. Okay. I hope this is clear, right? So what we did, we had to find the mass flow rate of air. We needed to find out the specific volume. Specific volume we calculated from perfect gas equation, and mass flow rate, for mass flow rate we took the help of this A and B. Okay, and this way we found out the power, right? Right. So this was your question number 9. So this comes out to be 67.38 kilowatts. Now moving on to next question. So the bed particles, it says that It's a numerical answer type question. It says that the bed particles of a medium size 390 micrometer, right, is fluidized by air under ambient conditions where air is 1.2, viscosity is this, density, so bulk density is given as this, and density of solid is given as this. You need to find out the minimum fluidization velocity. So how do we solve this? So 1, 2, 3, 4, 5, 5 things we have been given, right? So question number 10, solution. So bulk density has been given as this. Solid density has been given as this, right? Density of air has been given as ambient conditions, right? This. Then viscosity of air has been given as this. And the size of particles. Okay, size means its diameter. It is given as 390 micrometer. That is 390 into 10 raised to the minus 6 meters, right? So what we will do, so we need to find out the fluidization velocity, right? So for fluidization velocity, how can we find out? A, we can take help of Reynolds number. So m is your velocity. Okay. So from here we can find out fluidization velocity. But what is known here to us? This is known to us. This is known to us. This is known to us, right? But Reynolds number is not known to us. Okay. And what is Reynolds number? So there is one expression for Reynolds number. This, where C1 is your 27.2 and C2 is your 0.048, right? So this way we can calculate Reynolds number, but here AR, so this value we don't have, and this is, so this we don't have, so but this is equal to this. Okay, so this we know, 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 this we know. So this way, if we have AR, we can calculate RE, Reynolds number, and if we have Reynolds number, we can calculate fluidization velocity. So let's see this then. So first we will calculate AR. Okay, so AR equals to 1.2 2640, 2648 minus 1.2 into 9.8. G is your acceleration due to gravity. dp is your 390 into 10 raised to power minus 6 raised to power 3. Viscosity is 1.8 into 10 raised to power minus 5 square. So if you solve this, calculate this, this will come out to be, so I have already calculated it, this will come out to be 0.7. Okay, AR is this. Now, what do we need to find out? Reynolds number. Okay, Reynolds number is, so C1 27.2 square plus 0.048 C2 into AR 698.7 7 0.5 minus 27.2. Okay, C1. Yes. So if you solve this, this will be, please cross check the calculations. Okay. So this will be 4.46, right? So now we have Reynolds number value. Now we can calculate. So 4.46 equals to UM 1.2 into dP 390 into 10 raised to the power minus 6 divided by 1.8 into 10 raised to the power minus 5. Okay, this implies UM equals to, if you calculate this, this will come out to be 0.17 meter per second. So this is your answer to this question, right? For minimum fluidization velocity. Then we have lecture number 17. So just give me a 2 minutes break. So I'll be right back. Okay, so now we are into lecture number 17. So we are left with around 30 minutes. So we'll just move quickly. So this is on heat of combustion. Heat of combustion in closed and open system. Okay, open and closed system have been discussed. Then heating values have been discussed. Heating values we have discussed in previous lecture also. Then combustion temperature is there. Then combustion of coal is there. Okay, so what I have used to find out, so if you just see this numerical number 9, so B point that I have used in numerical number 9, so this has been discussed in under this heading, combustion of coal. Okay, so you can find it there only. Then is your liquid fuels and biomass. Okay, so in heating, heat of combustion. So basically, this gives you a this heading gives you an idea about how you can calculate your heat of combustion. Okay, lecture number 17, heat of combustion. So here topic like enthalpy of formation. So enthalpy of formation is an important element that is used to calculate all these heats, right? Heat of combustion. So this has been discussed, right? And these have been discussed in terms of your open system and closed system. And I hope you are all are well versed with what is an open system and what is an closed system, right? Open system is where you can mass can exchange across the boundaries, and closed system is where mass cannot exchange. But energy can exchange in your closed system, and in your open system, both mass and energy can exchange, right? Okay. Yes. So basic expressions like basic equating, right? The subscript R is for reactants and subscript R is for your products, right? So this is for your open system. And then for your closed system, only internal energy is there, right? Okay. So this was discussed in your heat of combustion. Then heating values. Next topic is your heating values. So for open system, we call it enthalpy of combustion. For closed system, we call it internal energy of combustion, right? Then how can we calculate? How can we find out? Sorry, heating values. So we can use calorimeters, right? So one such calorimeter is bomb calorimeter. Basic things that we should know. Okay. Then relation between your, so we have discussed it very loosely. Relation between high heating value and low heating value. So how do we do this? So low heating value is high heating value minus your mass of water into enthalpy of this latent heat. Okay. First is this, then is your Dulong and Pettit formula is there. Okay, which can be used to calculate high heating value, and from your high heating value, then you can further calculate your. Okay, so C is for mass fraction of carbon, H is for mass fraction of hydrogen, O is for mass fraction of oxygen, and S is for mass fraction of sulfur. Right, so this way you can find out high heating value. So this is about your heating values. Then next heading is your combustion temperatures. So what happens to your combustion temperature when your mixture is lean? And what happens to your combustion temperature when your mixture is rich? Yes. So this is in comparison to your stoichiometric conditions. So if you burn your fuel or coal in stoichiometric conditions, let's say in that case it has some temperature T. So comparing it with your lean mixture and your rich mixture, what is the effect on the combustion temperature? So in your lean mixture, the combustion temperature decreases because of what? Dilution effect. Okay. And what happens for your rich mixture? Again, again the combustion temperature decreases when you compare with your stoichiometric combustion. And why so? Because of incomplete combustion. right? So this is about your combustion temperature. And then there is adiabatic flame temperature, sorry, that I have discussed earlier also, which is in adiabatic conditions. If you burn your fuel, so the maximum temperature that it achieves is your adiabatic flame temperature. Then next topic is your combustion of coal. So in your combustion of coal, what happens to your carbon? It gives you this. What happens to your hydrogen? It gives you this. And for sulfur, it is this, sulfur dioxide. Now, if you want to have weight of oxygen that is required, that is in terms of carbon, if you see, in terms of weight of carbon, if you see, that is 2.76 of carbon that is required. For hydrogen, it is 8. For sulfur, it is as it is for sulfur, same as for your oxygen. Okay. Right. And now, because there is 23.2% of oxygen is there in your air. So if we want to talk about the amount of air we require, right? So what I have just written above is amount of oxygen that is required. So in terms of air, if we want, so how will we write? So theoretical air for 1 kg of fuel, W2 equals to WO2 divided by 0.232, right? So this way we can calculate the theoretical air, right? So this is about combustion of coal. Then last topic is liquid fuels and biomass. So in liquid fuels, so liquid fuels can come from your crude oil, right? And then one important point about your liquid fuels is flash point, right? So flash point basically is the temperature beyond which if we go for liquid fuel. So if we heat a liquid, we keep on heating our liquid fuel, and we bring it close to some flash, right? So beyond this temperature, if we go, your liquid fuel will catch fire, right? So that is basically the meaning of your flash point, right? Then, so this was one important term that was I felt was important in liquid fuels. Else is very basic that the lecture says that we use hydrocarbons. So liquid fuels are majorly hydrocarbons, right? So examples like alkanes, benzene. So all this have been given in your lecture, right? Then what is biomass, right? So, so bio, as we know, is life, right? So it's related to that only. So you all must be hearing about blending of fuels, right? With ethanol that has been produced from biomass. So this you must be hearing in your news. So that is same biomass, right? So there are two ways in which we can get fuel from biomass. Two major ways that have been discussed. One is your thermochemical conversion through thermochemical conversion. Next is your biochemical conversion. So in your thermochemical conversion, what we do, we heat the biomass, but in very limited amount of oxygen, right? So we heat the biomass in very limited amount of oxygen, and the product we get is your methanol or ethanol, right? So this is your thermochemical conversion. Then is your biochemical conversion, where you let your biomass degrade, right? Decompose in the absence of air. So if the decomposition is in the absence of air, this that is anaerobic decomposition. If it is in the presence of air, that is aerobic, right? So we do it using anaerobic uh, decomposition, and the products we get is methane and carbon dioxide, right? So this is your biochemical conversion. So this was about your lecture number 17. Then questions. So we'll quickly just go through this. So this question number 11 says that heating values for open and closed systems are known as dash of combustion and dash of combustion. So for your open system, this is enthalpy, and for your closed system, this is internal energy. Okay. So option A is correct. Okay. So this was question number 11. Then moving on to question number 12. It says that a lean mixture yields lower combustion temperature because of, so for lean mixture, whether this is dilution effect or incomplete combustion. So we have seen that for your lean combustion, it is your dilution effect, right? We have air in excess amount, which means lean means air in excess amount or your fuel in less amount. So B option is correct for this. Correct. I hope you remember this. Air, lean mixture and rich mixture. Okay. Then is your question number 13. Sorry. I believe question number 12 and 13 are same by mistake. All right. Then moving on to next question. So which of the following is correct definition of dilution effect? So this dilution we now want to quantify, right? The dilution effect that we see in lean mixture, we want to quantify it. So we have defined one parameter for that, right? So we have defined one term for that, that is dilution effect. So how do we define it? So four options have been given. So it's a ratio of air to fuel yes. So which is the correct option? So your dilution effect is dilution coefficient is this is your actual amount to the theoretical WT, right? Okay, WT I believe is theoretical, but I'll just confirm this. So I believe this should have been A option, theoretical. Okay, question number 14th. Okay, then next question is, so this is correct, right? That maximum temperature at which inflammable vapors exist. After this temperature, we will see flames. Okay, so A is correct. A option is correct. So we have seen what flash point is, okay, for liquid fuels. Then last question of the session. So which of the following is correct about thermochemical conversion of biomass? So it is done by heating with limited oxygen, heating with sufficient oxygen, by means of aerobic decomposition, by means of anaerobic decomposition. So we know that anaerobic decomposition is what? This is your biochemical. Aerobic we have not seen in our discussion, so we don't know about this. Then heating with sufficient oxygen we have not discussed, but we have seen that heating with limited amount of oxygen is thermochemical conversion of biomass, right? So in that case, A is the correct option. Okay. So this was it about this session. Okay. And so I'll conclude this session in that case. So there were two lectures. So we are discussing vapor power system still. This is third part of vapor power system. So the theme of today's this session was basically fuels and their combustion, right? So in your first lecture, you see coal and then types of coal, right? Grading of coal, then how different firing mechanisms are used, and in it, a major firing method or combustor is your fluidized bed combustor. So we discussed that, right? And one advantage, major advantage is that we can separate sulfur in fluidized bed combustor using your cyclone separator, right? Then is next lecture number 17, where we discuss combustion of coal, right? And the amount of air that is required to combust coal, right? And how we can calculate it, right? And then later we discussed very briefly what are liquid fuels, right? And then we at the end briefly discussed biomass and how we can get fuel from it. Okay, so this was at about session number 7. And I thank you for watching this session, and next session again will be on next Tuesday from 6 to 8 p.m., right? So you can either join this session live, or you can also watch the videos, recorded videos on YouTube also. So that is up to you. Okay. All right then. Thank you.